So after defining the trifocal tensor from the incidence relations of three views, we'll now move on to see that a fundamental geometric property that is encoded in the trifocal tensor is the homography between the first and the third view, or any of the two views, that is induced by the line, the back projection of the line in the third view, or in the second image in this example over here. We can see that more specifically, given a line correspondence, which we denote as L prime in the second image over here, this line, this image line is it back projects to a plane which we call pi prime over here, and this induces a homography together with the trifocal tensor, such that this homography can be used to transfer a point that is observed in the first image to the third image. We can also see that this particular back projected plane together with the trifocal tensor can also be used to define the same homography that can also be used to transfer a line that is observed in the first image to the third image without actually going through the computation of the 3D line L over here, or the 3D point over here in the first example. More specifically, the homography that is induced by the trifocal tensor and the back projected plane of the second image is given by this guy over here, H13. It's a function of L prime and the trifocal tensor because it's induced by the trifocal tensor over here, as well as L prime, that is the image line that is observed in the second view over here. In the subsequent slides, we'll prove that this is true. But before we do that, we can see that similarly, a line in the third image, which we call L prime prime over here, it's going to induce a homography together with the trifocal tensor that transfer a point from the first image, which we call X over here. It's going to transfer this view to the second image over here, which we call X prime. And here, these two, X and X prime, is going to be related by the homography H12, which we define over here, and we will see that this H12 over here, it's formulated by the trifocal tensor as well as the line correspondence L prime prime in the third view. Now we'll go on to prove that the homography between any two views is induced by the trifocal tensor and the back projected plane from the image correspondences, from the line correspondence in the third view. More specifically, we learned from the earlier lecture that the homography map between the first and third image can be written as x prime prime equals to h multiplied by x, where h here is the homography that transfer the point from the first view here, which we call x over here, to the third view. So the x prime prime here is equals to h multiplied by x, which is where we are transferring the point from the first image to the third image over here, which we call x prime prime. And the similar relation can also be obtained from earlier lecture for a line between the first and the third view. If we were to transfer a line from the third view into the first view, this means that it's this way around. We can see that the relation here can be obtained as L equals to H transpose L prime prime. And we also saw earlier that the incidence relation between the three line correspondences L, L prime, and L prime prime in the respective three views, it's given by Li equals to L prime transpose multiplied by the trifocal tensor Ti multiplied by L prime prime, where Li here, call that this is the ith coordinate of the line L, and Ti, it's the 3x3 metric that corresponds to the trifocal tensor. And a direct comparison of this incidence relation that we have derived earlier on, as shown here in this equation here, and the homography equation that we have learned in the earlier lectures, shows that this L prime transpose multiplied by Ti over here, it defines a homography, or more specifically in this particular notation over here, since we are looking at Li, that is the respective coordinates of the ith coordinate of the line. What this means here is that L prime transpose multiplied by Ti will give us the ith column of the homography matrix over here, and which we can rewrite in this particular equation over here. So here the particular column Hi is given by Ti transpose multiplied by Li. Since there's a transpose over here, this means that we transpose this guy over here, and this is the relation that we will get for every single column. So, which means that if I want to compute for H1, I will simply take a T1 transpose multiplied by L1. And similarly for H2, that would be T2 transpose multiplied by L2. And we'll do the same for the third column of the homography matrix. So in similar vein, we can also rewrite the homography between the first and the second view as L transpose equals to L prime transpose multiplied by H, where H here defines the homography between the first and second view, which we denote as H12 over here. And we'll see that a direct comparison with this guy over here, the incidence relation over here, Li equals to L prime transpose multiplied by Ti multiplied by L prime prime over here, we'll be able to directly obtain this relation where Hi over here, which relates the homography, this is the ith column of the homography matrix that relates the first two view. It's simply given by Ti multiplied by L prime prime over here. Now we can take the cross product of the incidence relation that we have derived earlier on to eliminate the unknown scale in between this, that is inside this particular incidence relation, to get the homogeneous form as we see in this particular equation over here. So this is simply taking the cross product of L transpose and L. So what this means is that we can let's rewrite the cross product over here as this guy over here, cross product multiplied by L transpose, and we can do the same on the right hand side of this equation. As a result, we will get this form of the equation over here that is equals to 0, and the unknown scale, which let's say we call it lambda over here in this particular equation, it can be eliminated. Or more briefly, instead of writing T1, T2, T3 in the square bracket shown here, we can write in a short form where it's simply denoted as the square bracket of Ti over here. And so this means that these two equations here, they actually means the same thing, but this is the shorthand of the longer form of the equation as shown earlier on here. And the symmetry between L prime and L prime prime also means that we can take the transpose of this guy over here, and hence we can see that L prime prime here and L prime swap position, and we have to add a transpose and remove the transpose and L prime. But the relation will still remain the same. The cross product of these two terms over here is still going to be giving us 0 over here. And here by writing the equation into these two forms over here, we eliminated the unknown scale. And now the relation that is shown by these two equations over here would be simply relating the image correspondences L prime and L prime prime and the trifocal tensor without any other unknown parameters in this particular equation over here. We can do the same thing for point line correspondences. This means that in the first image I would have a image point, and then in the second image I have a line correspondence that is what I call L prime over here, and in the third image I would have another line correspondence which is what I call L prime prime over here. So what this means is that point and the line image correspondences, they back project to an intersection in 3D space of a 3D line which we call L. So this particular 3D line, it's the intersection of the back projection of L prime and L prime prime from the second and the third view, this particular line, this 3D line over here, has to intersect with the ray that is being back projected from the image point X over here. So notice that earlier on I said that the line correspondences from any two views would not be enough to constrain the two image between these two views. In this particular case, if we were to ignore the point correspondence over here, then there is not enough constraint for us to constrain the two views, because simply any two back projected planes by the two respective view would intersect at any line. It will always intersect at a line, and this is not enough to constrain the relative pose or the relative relation between the two views. But now we have a third view over here, which is denoted by the back projection, the light ray that is being back projected from the image point correspondence over here. And we know that this particular image point correspondence, it must back project to a 3D point that sits on this particular line, that is an intersection of the back projected plane from the second and third view. Hence, the third view over here, back projected light ray over here from this point correspondence, helps to constrain the three views together. And in short, what this means is that having the third view over here is simply acts as a constraint to constrain the relative positions, the relative poses of the image views within the three different views over here. And now we know that the point on a line where we have learned in the first lecture must satisfy this dot product equation over here, the incidence relation over here, where the dot product of the point and the line must always be equals to 0. And now let us rewrite this particular dot product, because this dot product can be seen as x1, x2, and x3 multiplied by L1, L2, and L3. Notice that I'm using a superscript here to represent the row, the coordinates of the respective of the ith row in the point, and I'm using the subscript here to represent the ith coordinate of the line in the respective column over here. By doing a dot product of these two entities over here, the point and the line, essentially what we'll get is this guy over here, x1 multiplied by L1 plus x2 multiplied by L2 plus x3 multiplied by L3, which can be rewritten into this form over here. So it's simply going to be the summation over the ith index xi multiplied by li, and this has got to be in equals to 0. So we'll make use of this notation over here to denote the dot product of a point and a line here. And now we also know from earlier derivation of the trifocal tensor that the ith coordinate L is going to be given by L prime transpose Ti multiplied by L prime prime over here. And this can be now put into this particular incidence relation of the point and the line. So we can see that now this becomes summation of I x I L prime transpose Ti L prime prime, where we substitute this guy over here with this, since Li is equals to this term over here. So and we notice that L prime and L prime prime, they are independent of the index, so we can actually factorize them out and to rewrite the summation of I as this term over here, summation xi multiplied by Ti, and we can put the bracket outside here, and then we pre-multiply by L prime and post-multiply by L prime prime. And since the dot product of this guy over here has to be equals to 0, it also means that this particular equation over here has to be equals to 0. Hence, we have derived the relation, the incidence relation of a point line correspondence, which is also free from any unknown scale or any other unknown parameters over here. The only unknown over here would be entries in the trifocal tensor. So the correspondences here would be what we observe from the respective images. which is more precisely a point-line-line correspondence. We can also derive the same thing for point-line-point correspondence. What this means is that in the first view, I would have a point that back projects to a ray, and the second view, I would have a line, which I denote as L prime, that back projects to a plane, and the third view over here, which it's going to be a point correspondence, which I denote as X prime prime, that's going to back project to the light ray over here. And this X and L prime and X prime prime here, they are correspondences. What this means is that they better meet at certain parts of in the 3D space, as illustrated by this figure over here. We can see that the point and the point, they will meet at a point, and they will also meet at a 3D line that gives rise to the projection of this L prime here in the second image. And what's interesting here is that we can make use of the homography relation that we have derived earlier on to get the point-line-point incidence equation over here. So more specifically, we can see that the back projection of L prime, it's going to form a plane, which we can call pi prime over here. And this particular plane, it contains both the line that gives rise to this particular L prime in the second image, as well as the 3D point that is from the intersection of the back projected ray from the first image and the third image, specifically from the point correspondences of X and X prime prime over here. Since the intersection, which is the 3D point that gives rise to the 2 points in the first view and the third view, sits on the plane. What this means is that there is a homography that relates the X prime prime and X over here. So we can write this relation: X equals to H multiplied by X prime prime over here. And this is what we have seen earlier on, which is the homography between the first and third view, and is induced by the back projected plane of L prime, as well as the trifocal tensor that is given by this equation over here. So we can simply write this using the homography relation: X prime prime equals to this guy over here multiplied by X, which can be rewritten into this particular form over here. What this means is that because L prime over here, it's common to all the three trifocal matrix over here, T1, T2, as well as T3. What we can do is that we can pull this out, factorize this out, and simply write L prime on the right hand side over here, and then we push X into the coordinates over here, into the respective trifocal tensor entries here. And we can see that this can be rewritten in the same form as what we have seen earlier on, except for now Ti represents the respective entries of the trifocal tensor. It's actually a 3x3 matrix over here, and the summation over xi, this xi over here, simply refers to the ith entry of the image point. We can make use of this to represent the homography relation. Now, the homogeneous scale factor from the homography relation can be eliminated by taking the cross product of x on both sides. So we can see that here, given this particular equation over here, by taking the cross product of x on both sides, you can see that this guy over here, this term over here, will become 0, and hence the unknown scale of this homography equation can be eliminated, and this gives rise to this particular incidence relation, homogeneous incidence relation that is shown in this particular equation over here. So a similar analysis can also be done instead of using a point-line-point. It can also be done using a point-point-line relation. We can see that the relation is almost the same, except for now the point the second view contains a point, which we denote by x prime over here. And the third view, instead of having a point, it becomes a line, which we denote as L prime prime over here. But the second view is still a point. So this particular summation over here that arose from the homography that multiplied by x, it still remains. Now, we can also do the same thing to derive the incidence relations between three views, which contains a point correspondence. So what this means is that instead of having a line on all the respective three views, now each view contains a point that back projects to a light ray, and the three light rays over here, it must meet at a single point in the 3D space, which is the 3D point capital X over here that gives rise to the projection of X and X prime and X prime prime in the respective three views. So here we'll show that it's the incidence relation over here is given by this particular equation over here. So here's the proof on why is this true. We know that the line in the second image, which we denote as L prime over here, it can be expressed in this particular incidence relation. So this is what we have seen earlier on. It's a point line point correspondence or incidence relation, where the first point here is represented by x, and then in the first view, the second view, it contains a line which we call L prime over here, and the third view, it contains a point which we call x prime prime over here. So this is what we have seen earlier on, and let this particular line over here, which we denote as L prime, so pass through some points which we write as x prime over here. And so this line over here, it can be written as the cross product of 2 points on the line. So what this means is that I have in the second view, this is my image 2 in the second view. I have a line correspondence which I denote as L prime, and this line here, it's actually given by 2 points which I denote as x prime and y prime over here. So the cross product of these 2 points would give me L prime, and I can simply write this cross product as into this metric multiplication form, and consequently we can substitute the cross product of these 2 points back into the point line point incidence relation to substitute this L prime over here, and this is what we get, this particular equation over here, where this term over here represents L prime transpose. Now, what's interesting here is that we know that the point line point, which is given by this guy over here, so this is the same as what we have seen earlier on here. The incidence relation here is going to be true for every line L prime here, passes through any point x prime over here. And so this means that this particular equation here, which represents the incidence relation of point line and point, where the line is being represented by the cross products of any 2 points that lies on this line L prime, is independent of the second point on the line, which we call y prime over here, which implies that since it's independent of y prime here, where y prime is generally not equals to 0 over here. So in order for this relation to be true, then the product of the remaining terms over here, it must be equals to 0. Hence, we can rewrite this relation into this relation over here, where the product of the remaining terms equates to a 3×3 0 matrix over here. And this, as a result, gives us the incidence relation between a point and point correspondences between the three views. Now, here's a table that summarizes all the point and line incidence relations that we have seen earlier on. So it consists of line, and this is what we have seen earlier on. It all started with this incidence relation, the equation that we have derived when we derived the trifocal tensor. So taking the cross product to eliminate the unknown scale, we will get this guy over here. Then we look at the point line correspondence, where the first view has a point, and we get this particular equation over here, and so on and so forth. So we saw point line point line, and as well as point and point correspondences in the respective three views. Now, the next thing that we can derive from the three-view relation would be the respective epipolar lines on the respective images in the three-view. Now, suppose that X is a point and in the first view, and L prime and L prime prime are the corresponding epipolar lines in the second and third view. So what this means is that I have a first view which contains a point which I call X, and then in the second view I have a line, because we know that the back projected ray of this particular image point X over here, the actual 3D point can be anywhere on this particular back projected line. So when transfer of the point from the first view to the second view is going to become an epipolar line over here, which means that this is simply the projection of the back projected ray from the image point X over here. And we're going to denote this as L prime, and this is what we call the epipolar line. So similarly, in the third view, we are going to forward project this particular light ray onto the third view, and this is going to define another line over here. This plane and the image plane is going to intersect at this particular line over here, which we call L prime prime over here. And this is going to be the epipolar line that is formed by a point correspondence in the first image. We'll do the proof later, but we'll just state that the relation between the epipolar line and the trifocal tensor, as well as the image point that gives rise to this particular epipolar lines, it's given by this equation over here. So this is between the first and second view, and what it means here is that I'm back projecting the point to the ray and then projecting this ray onto the second view to get the epipolar line over here. And similarly, this null space equation over here, it's going to define the epipolar line and the trifocal tensor, as well as the point that in the first image that gives rise to the epipolar line in the third view. So this is going to be the first and third view. And consequently, from these two equations over here, we can see that since this is a null space equation, we can see that the epipolar line in the second view that is formed by a point in the first view, which call X over here, it's given by the left null vector of this equation over here, which simply consists of the image point in the first view and the trifocal tensor. And the epipolar line in the third view, which you call L prime prime here, is solved as the right null space vector of this particular matrix equation over here. This is a 3x3 matrix. They are both the same over here. And what this means is that L prime is solved as the left null vector, and the L prime prime over here is solved as the right null vector of this matrix, this 3x3 matrix over here that we denote in this case. And now we show the proof for the left and right null space for the epipolar line as shown earlier on. We'll consider a special case of the point line correspondence in three views over here. So now in this particular case, we can see that the point in the first image, which we denote as X over here, back projects to a light ray, which contains the 3D point over here, which we call capital X over here. And now we're assuming that the line correspondence in the second view over here is formed by the plane pi prime over here, that is formed by the projection of the back projected light ray of the point correspondence in the first view, which called X over here. So this line over here is going to back project to a plane that is seen by the second camera C prime over here, and the intersection over here is going to form L prime. And we learned in the lecture in fundamental matrix that this intersection of L prime over here is what we call the epipolar line. We can see that this particular plane over here that contains the camera center of both C and C prime, the first and second view, as well as the light ray formed by the back projection of X over here. It's what we call the epipolar plane that relates the first and second view. And suppose that X is a point on the plane pi, pi prime over here. So X is the point, which is actually the 3D point of this that gives rise to this particular image projection in the first image, point projection in the first image over here, that is denoted by a small x. We further denote the array that is defined by X, which is this capital X over here, the 3D point, and C, the camera center, the first camera center over here, this light ray over here, will sit on this particular plane, which is the epipolar plane. And hence the line L prime that is formed by the intersection of this epipolar plane and the second image would be what we call the epipolar line. Let's denote this by L prime. So we will also further denote a plane pi prime prime that is formed by the back projection of a line L prime prime in the third view. So this is the third view. And note that in this particular case, L prime prime can be any line on the third view that is in the incidence relation with the point in the first image and the epipolar line in the second image. And let's call the intersection of this back projected plane from the line correspondence in the third view L prime prime with the epipolar plane as this line over here, which we denote as capital L over here. And hence, this gives rise to a three-way intersection between the back projected light ray from the first image of the point and the back projected planes from the respective line correspondences, which is denoted by L and L prime respectively. This actually constitutes what we have seen earlier on, the point line correspondence, which must satisfy this incidence relationship that we have derived earlier on. So now the important part to note is that this relation must be true for any L prime prime, for any line in the third view. Notice that we didn't put any constraint that this L prime prime over here in the third view must be any particular line. So whereas in contrast in the second view over here, we define very strictly that this guy over here, L prime, is going to be the epipolar line because it has to be formed by the projection of this light ray from the first image onto the second image. But this L prime prime over here in the third view can be any arbitrary line. So what this means is that the following relation must be true. Since L prime prime can be any line, and in general this L prime prime here will not be zero. So what this means is that product of the remaining terms over here, which is denoted by this guy over here, it has to be equals to 0 in order for the incidence relation here to be true. And the same arguments holds even if the rows of L and L prime reverse. So since we derive a particular equation over here by making the assumption that L prime in the second view is the epipolar line, and we didn't make any assumptions for the line in the third view. As a result, we get this particular equation over here, this particular relation over here. We can also swap the rows of L and L prime. This means that we insist that L prime prime over here it's equals to the epipolar line. And L prime over here, we relax it to say that this is not going to be an epipolar line, but it can be any line in general in the second view. So now we can see that if this is any line in the second view that is non-zero, what it means is that this relations here, product of the remaining terms over here, must always be equals to 0. Hence, we can rewrite the equation here in this particular form here, where L prime prime now in this particular case is the epipolar line of the third view, and hence we get these two equations that we have seen earlier on here, which is equivalent to the left and right null spaces of the 3 by 3 matrix over here that is formed by the image point correspondence in the first view and the trifocal tensor. And this completes our proof. Now we know that given a point which we denote as x in the first view, this is going to give rise to the epipolar line which we call L prime in the second view. And so as x varies here in the first view, so that means that if I have different x over here, it's going to give rise to different epipolar lines. And we know from our earlier lectures when we learn about fundamental matrices and epipolar lines as well as epipoles, that these different point in the first view, it's going to give rise to different epipolar lines in the second view. But all these different epipolar lines, they must intersect at a common point. And this common point is what we call the epipole. And we are going to denote this epipole in the second view as E prime. So similar relation can also be obtained from the third view, where a point correspondence in the first is going to transfer to different epipolar lines in the third view. So we are going to denote this as L prime prime, and this particular epipole here is we are going to denote it as E prime prime. And hence the epipoles in the second and the third view can be computed by the intersection of the various epipolar lines that was obtained by varying the point in the first view. And or three convenient choices for x over here would be the homogeneous coordinate of 1, 0, 0, 0, 1, 0, as well as 0, 0, 1. The reason why these three are convenient choices because we have to compute the left and right null spaces of this equation over here in order to get the respective epipolar line. We can evaluate by, for example, taking this 1, 0, 0 over here as x. We can see that the x1 over here would become 1 multiplied by t1 plus 0 multiplied by t2 and plus 0 multiplied by t3, and this would simply give rise to only t1 over here. So what it means here is that the summation when the point is equals to 1, 0, 0 over here, then we simply just need to compute the left and right null space of T1 in order to get the epipolar line in the second and third view that corresponds to this particular point over here. So similarly, 0, 1, 0 would also be a good choice, and this would result in computing just T2 as well as 0, 0, 1. This would result in just computing the left and right null space of T3 over here. And now, once we have obtained the three epipolar lines, that is from these three convenient choices of the point in the first image, we can simply compute the epipole as the common intersection of these lines by the left and right null space. So E prime over here, which is the epipole in the second image, would be the intersection of the three epipolar lines that comes from 1, 0, 0, 0, 1, 0, and 0, 0, 1 from the first view.